So I've talked a little bit about this idea of enthalpy. That enthalpy will allow us to establish whether or not a reaction is exothermic, that is giving off energy to the surroundings, or endothermic, that is taking energy from the surroundings. And you might be asking, well, is there a way that we can easily perform a reaction and figure out whether or not it's exothermic or endothermic, and maybe even measure to what degree or what the magnitude is of the exothermic nature of the reaction or the endothermic nature of the reaction? And in a high school chemistry lab, this would be possible if we could find something that was readily available, cheap, and a good insulator. A styrofoam coffee cup, you say? Yeah, that just might work. In fact, we refer to this as coffee cup or constant pressure calorimetry. And the way that it works is that we perform a reaction inside this coffee cup in a solution. And the solution, or the solvent in the solution, is water. And since we know a lot about water in terms of how it behaves in response to energy transfer, we can then figure out, based on what happens to the water, whether or not the reaction is exothermic or endothermic. So we're going to use water, which we treat as the surroundings, to establish the enthalpy change of the system. So whatever energy transfer is from the reaction or the system into the water, that's going to allow us to figure out whether it's exothermic or endothermic. If the temperature of the water goes up, then the reaction must have released energy. If the temperature of the water goes down, then the reaction must have absorbed energy. Now, there are a series of calculations that we go through in order to establish the magnitude of this reaction in its endothermic or exothermic nature. So the first thing we're going to take a look at is what this coffee cup calorimeter sort of looks like. And really, it's just that, a coffee cup. And we have a lid to try and make as close to a closed system as we can. And then we're going to fill it up with water. And what the water is going to give us is going to allow us to determine the energy transfer to or from the water if we can measure a couple of things about this water. And the relationship that we use, or the equation that we use, is Q equals mc delta T. Now, the mass is the mass of the water. And it's important to note that it's the mass of the water, because we're figuring out the Q of the water, and not the mass of the reactants. So it's the mass of the water. Now, most of the time, we're going to be adding water in terms of a volume, that is, the number of milliliters that we put in. But since we need the mass, we have to remember that water's density is equal to 1 gram per milliliter. So if we put in 100 milliliters of water, it's going to have a mass of 100 grams. We're also going to use the specific heat capacity of the water to help us in this calculation. And we're going to remember, we're going to use it enough that you're going to remember or get to learn that the specific heat capacity of water is 4.184 joules per gram degree Celsius. But of course, this is a value that you can always look up. Now, in order to use these two values, we have to make the assumption that the solution is dilute enough to effectively have the properties of water. And in most cases, that's a pretty safe assumption to make. We're then going to perform the reaction and measure the temperature change of the water. And so this is where our delta T comes in. Delta refers to a change in, and T refers to the temperature. So our delta T here is the change in the temperature of the water. If the temperature of the water goes up, it's going to be a positive delta T. If the temperature of the water goes down, it's going to, of course, be a negative delta T. And in order to do this, we make the assumption that all of the energy transfer is to or from the water, and the coffee cup is a perfect insulator, which is obviously not true, but it's pretty close. And in a high school laboratory, it's pretty safe to make this assumption. Now, once we've done that, we have to have the understanding that any energy transfer to the water is from the reaction, or any energy transfer from the water is to the reaction. So we understand that any heat lost to the water is from the system, and any heat gained from the water is to the system. So we say that the heat of the system is equal to the negative heat of the surroundings. That is, whatever heat was gained or lost by the water is lost or gained by the system. Now, this is a straightforward calculation to make, but it's one that students sometimes forget. So you always have to remember, if we're trying to figure out the heat change from the water to the system, we have to change the sign on that Q value. Then, here comes our old pal stoichiometry. We have to know the balanced chemical equation for the reaction that's proceeding inside our coffee cup calorimeter. Then we have to know the mass and the molar mass, or the volume and the concentration of the reactants that we're dealing with, in order to establish which one of the two is limiting. because just like a chemical reaction in which we're trying to produce an amount of product, the same sort of thing goes for a thermochemical reaction. The amount of reactant is going to determine how much heat is lost or gained by that system. The greater the amount of the limiting reagent, the greater amount of energy is going to be given off or absorbed by that reaction. And that sort of just makes sense. If we up the magnitude of the reactants, we should have a greater amount of energy released, or vice versa. So we're going to use stoichiometric calculations again to determine which one of our reactants is limiting. And then we're going to obtain that molar value. That's going to be important because in our next step, we are going to establish what the enthalpy change is for our overall reaction. So once we've had our Q from our second step, and we have our N, or our number of moles of our limiting reagent from our third step, we're going to combine these two in the following reaction, that is, or the following equation. That is, the delta H, or the enthalpy change of the reaction, is equal to the Q of the system divided by the number of moles of our limiting reagent. And so that's going to give us a value for our enthalpy change, which we are then going to put into our balanced chemical equation to arrive at a thermochemical equation. So now we can represent these equations that we perform empirically or experimentally as thermochemical equations. And if we perform these calculations, we can even express the magnitude, the number of kilojoules that we release per mole of reactant. So try and go through these steps with an example problem and see if you can come up with a way of representing thermochemical equations or maybe even an enthalpy diagram.